Hello, everyone. In this root lab session, I'll talk about our open source face mask detection algorithm. We developed this algorithm together with my colleague Ton, and the main motivation behind this algorithm was to detect, for example, unmasked faces in crowded places like shopping malls or train stations, hospitals. And in this session, I'll talk about how we built the modeling, which techniques did we use for the modeling part. And secondly, I'll talk about how did we validate the performance of the model. And at the third section of this presentation, I'll talk about how to call this deployed version of this model. And this model is freely accessible for you, and it's already deployed. So let's first start with the model overview, like the general model workflow. So our model accepts an input image like this, and then this input function is transferred to the face detection algorithm. And the face detector detects the faces in a given input image like this. These two faces are detected. And then in the second step, the detected faces are cropped like this. And then finally, these cropped faces are given into the classifier model. And this classifier model predicts either the face wears a mask or not mask. As you see, it detects that this person, me, is masked, and my wife is detected as not masked. And so let's first start with which model and why we used, which model did we use in this face detection algorithm. So in this context, we need two important requirements. The first requirement is that the algorithm needs to be very powerful, because when someone puts a mask on his face, then his face is almost covered, like the mouth or like nose features are not seen by the model. So it needs to be powerful enough to detect the masked faces as well. And the second thing is it needs to be very fast. It needs to detect the faces almost real time, because one cannot wait like 5 minutes to detect the masked or not masked faces. And within this context, we did a literature research, and we find out that RetinaFace Model satisfies these two requirements. And in the RetinaFace Model paper, it is written that it's the state-of-the-art face localization algorithm that runs on real time on a single CPU core. And as you see, we also share the execution time of this model. And this model runs around like 3.7 FPS in a single CPU. And if we use GPU, this speed can increase up to 20.7 frame per second. And here you see the world's largest selfie. And this RetinaFace model almost detects all the faces. As you see here, there are very tiny faces, and most of them are detected correctly. So that's why we prefer to use this neural network-based RetinaFace model. And in the second phase, as I said, we also built our own classifier. So the detected faces needs to be classified whether they have a mask or not. And in this case, we trained our own algorithm. And for this training, we need a training dataset. And we prefer to use VGGFace 2 dataset. And the main advantage of this dataset is that there are too many identities from different ethnicities, genders, or age groups. So it will provide us a global model instead of just a local regional model. And the good thing is each identity, like each identity that you see here, has approximately have like 360 images. So it provides us variety as well. And all the photos are captured in the wild. So these photos are natural. And yeah, there is a problem in this data set, as you might guess. So there are like we sampled from this database, this dataset as like 2,000 not masked faces, but there is no masked face in this dataset. So the dataset is highly imbalanced. And one may ask why you didn't Google it. You didn't Google like masked faces. The issue was that most of the images in Google has copyright, and it's really hard to find like 2,000 images that are freely available. So as a solution, we thought that if Instagram uses like these artificial glasses on like people, if they are able to put these glasses, then why not we put the artificial masks on a face to generate our own synthetic data? So how can we put masks on someone's face? We need to use the facial landmark coordinates. So in this case, we use the nose coordinates and the chin coordinates to put the artificial mask. And to find the facial landmarks, we use DLIB library, which is written in C++. So this is a machine learning library, and it also has this facial landmark detection algorithm. This algorithm is a ensemble tree-based algorithm, and it predicts this 6 to 8 X and Y coordinates in a face. And yeah, these are the detected facial landmark coordinates. And the good thing about this algorithm is that even if, for example, I cover my eyes with stars like this, and it's still able to predict the location of my eyes. And in the end, as I said, by using this nose and chin coordinates, we artificially put this mask onto a person. And to increase the variety, we use 11 different mask templates that has different shape and different colors. And most of the time, this artificial mask algorithm worked quite well. As you see in different orientations, the face is covered with mask. But in this case, the last one, the performance is very bad because the person is really like from the side profile. So that's why it didn't work well. But overall, the overall performance was good enough. So now our training set is ready. We now have 2,000 not masked faces and 2,000 artificial masked faces. So we are ready to train our algorithm. So what algorithm did we use? I'll explain which algorithm did we use in this section, and we used transfer learning using MobileNet V1 architecture. So I'll explain what is transfer learning in the next slides, but briefly, in transfer learning, there is a pre-trained algorithm, and from that pre-trained algorithm, you transfer the learned weights from that algorithm into your specific algorithm. In this case, our specific algorithm is the mask or not mask classifier. And the general, the pre-trained algorithm is the MobileNet V1 architecture. So the MobileNet V1 is a neural network-based architecture. And as you might guess from the name, like MobileNet, it is mainly designed for mobile or embedded devices. So it's very lightweight, and it works quite fast in these embedded devices. And its main purpose is to predict 1,000 different objects. So the pre-trained algorithm ideally detects the objects. And now we will use this MobileNet algorithm to detect masked or not masked faces by using transfer learning. So what is transfer learning? So as I said, this MobileNet V1 architecture is trained to predict these 1,000 objects, and ImageNet dataset is used during the training. This dataset has also 1,000 different objects, as you might guess. And I also want to highlight this final layer in the neural network of MobileNet, because this final layer predicts the score of these 1,000 objects. And now we will use this transfer learning to predict either masked or not masked. So we will not predict these 1,000 objects. So in transfer learning, we don't need to use this final layer because we will not predict these 1,000 objects anymore. And instead, we are removing this layer and we are adding new additional neural layers to increase the performance of predicting the target masked or not masked classes. And in transfer learning, we get the pre-trained MobileNet V1 as it is, like this. We don't touch any weights, and we add additional new layers. And these new layers are trained with our own training set as we prepared. And in these layers were trained with ImageNet dataset, as I say. And optionally, we can also fine-tune the last N layer. So in our case, we fine-tune the last 4 layers, these layers, by using our training set as well. So as a summary, these layers, the first N layer is trained with ImageNet dataset, and we didn't touch any of these ways. And we fine-tune these 4 layers, and also we retrain these new layers from scratch. And what's the advantage of this transfer learning? The best advantage is that we don't need to retrain everything from scratch, and it saves us a huge amount of time. So all this network is trained just under 2 minutes. So it's a great advantage, and it provides a very decent results for us. And the implementation of transfer learning is also quite easy. Thanks to TensorFlow Keras, this MobileNet class can be imported with the pre-trained weights. And here we set the weights as ImageNet. It means that the network is trained by using ImageNet dataset. And as I said, we don't include the latest layer, the top layer, because our main purpose is to classify either masked or not masked faces. And here we set the input shape of the given image. So it's the image width, image height, and the 3 is the number of channels like red, green, and blue. And in this step, we are defining the workflow of this transfer learning. So we are defining these steps. And more concretely, the first step is the MobileNet, the pre-trained MobileNet base model.output. It's this entire block. And the second one is the global average pooling 2D layer. It's a dimension reduction layer. And additionally, we had another dense layer that has 128 neurons. And in the final stage, the additional layer is one dense layer, which has a sigmoid activation function. So it provides us a value between 0 and 1. And if it is close to 0, if the prediction is close to 0, it means that the person is not masked. And if it is close to 1, it means that the person is masked. So as I said, these 3 layers here represent these new layers. And finally, here we are telling the model that you can also fine-tune the last 4 layers. So we are telling the algorithm, we are telling Keras that you can fine-tune these final 4 layers by using our own training set. And we are also saying that don't touch the first N layers. So these are already trained by ImageNet dataset. So as you see, it's quite easy to use transfer learning. And now I'll talk about the validation part. So we see 2 different models like face detection and classification. Now let's see how they performed. So how did we prepare our validation and test set? As you might guess, we cannot use artificially masked faces in the real validation because otherwise it doesn't make sense to understand the performance of the model. And in this case, we find out 273 images from unsplash.com and pexels.com. These websites provide us free license to use these images. And among these images, we extract like 573 different faces. And also for the validation purpose, we need to manually label all these images. We need to manually label the ground truth box like this, the green box, and we need to say either the person is masked or not masked. And during this manual labeling phase, we use makesense.ai. This website, this web application provides us a very easy manual labeling. You just draw this rectangle, the ground truth box, and it automatically extracts the coordinates of the ground truth. And you can also manually label whether the person is not masked or masked. And by using this website, we labeled all these faces. And now for the in the first step, we check the face detection. We check the face detection performance. And we use intersection over union metric for this validation. This green box is the ground truth box, and the red one is the predicted box by the algorithm. And if the intersection of these two boxes here, if the intersection of these two boxes divided by the union of these boxes greater than 0.5, then it means that our prediction is correct. So in this case, as you see, the intersection over union is obviously greater than 0.5, and we can say that this prediction is correct. And I want to show you some of the correct and incorrect predictions. In this case, for example, all the faces are correctly identified and correctly detected, and their intersection over union score is greater than 0.5. But in this case, for example, there's the ground truth box here, but the face detector couldn't detect the face. But also in here, there is no ground truth box, but the face detector says that there is a detected face here for some reason. But overall, the general performance of our face detection algorithm was quite good. Among 251 ground truth boxes, like faces, we correctly predict 94%. And personally, I find this score is very good because most of the faces are masked, and even if they are masked, this face detection algorithm predicts this very accurately. So what about our classifier validation? As I said, if the score is close to 0, we classify it as not masked, and if it is close to 1, we predict the faces as like masked. And at this point, we put the threshold as 0.5. And for 0.5 threshold, our accuracy was 90%. And this is the confusion matrix for a given 0.5 threshold. And also for the other threshold like combinations, we also prefer to draw this AUC ROC curve, and our AUC metric is found as 0.97, which is a good score because it's very close to 1. So for different thresholds, our classifier classified not masked or masked faces quite accurately. And what about the overall evaluation? So the overall evaluation includes both detection and the classification. So in masked faces, there are 115 masked faces. And among these faces, 105 of them are identified and classified correctly. And 5 of the faces are identified by the face detection algorithm, but they are classified as wrong. They classified it as like unmasked. and 5 of the images are detected doesn't detected by the face detector algorithm. And in unmasked faces, we had 136 different faces. And among these faces, 118 of them are correctly classified and identified by our model. And 9 of them is identified, but the classifier predicts it as masked face, which is wrong. And finally, the 9 of them is not identified at all. And as you see, these numbers are same, but it's totally by chance, and it doesn't mean anything. And now the best part, the deployment part. So we used Dploy.ai deployment platform to deploy our model. So this Dploy.ai provides us a very easy model deployment. And currently it's in alpha stage, and in alpha stage users cannot deploy their own models, but they can call the already deployed models. And our model is one of the deployed model, as you see. Yeah. And I'll show you how you can call the deployed model. So here is the Dploy.ai website. You click to Model Hub. And from here, you can click face mask detection. And here you see the instructions about calling this algorithm from your local. So by using a simple QR command, you can provide your image and get annotated image whether you have a you wear a mask or not. And here there are some of the example images that you can try. And for example, we choose this image and let's call the model. And as you see, it's tell us that these persons are masked. And what about this one? Yeah, as you see, again, the person is detected as like masked. And the good thing is the face is almost like covered, and it's most of the time hard to detect these covered faces, but our algorithm successfully detect the face. And what about other persons having no mask? Yeah, and it classifies it correctly, like this one or this one, this one. Yeah. And if there is no face, like this one, so the model doesn't annotate anything. And I also want to show you how you can how we deployed the model thanks to Dploy.ai. So as I said, it's super easy to deploy your models thanks to Dploy.ai. You don't need to deal with any Kubernetes configurations or like Docker configurations. All you need to do is to write this deploy endpoint hashtag at deploy endpoint annotation to your endpoint function. So Dploy.ai understands that this function will be used by the API, and when you post a data to your deployed API, it will be the this body argument, and the return function will be the response of the API. And finally, before I finish the presentation, I want to give some useful links about this project. So you can find all the implementation, all the source code of this model in our Data.io GitHub page. And you can find the deployed model in app.dploy.ai in model hub page. You will see the face detection algorithm. And if you want to call this model from Python, you can visit this github.com Dploy.ai, deploy examples repository. There are very good examples how you can call these deployed models from Python. And thank you very much for your listening. And if you have any questions, please feel free to write your questions under the comment section, and I would be very happy to answer them.